Linear algebra. Lecture 5. And we've been studying Gaussian elimination as a method to solve systems of linear equations. And systems of equations is plural. It means we always have at least two equations. Otherwise, there's just one equation is pretty straightforward. So what I want to do is introduce the standard machinery for dealing with linear equations and Gaussian elimination. That is matrices. So in the notes, this is chapter 2. So this is a big deal. Oh, sorry. Yeah, I am recording. Matrices are something we use all the time in linear algebra. And what is a matrix? So an m by n matrix, and then T(R)(x) is simply a rectangular array of numbers with m rows and n columns. So for example, a 2 by 3 matrix might be 7, 2, 0, minus 5, 1, 3. This is a 2 by 3 matrix. It has 2 rows of numbers and 3 columns of numbers. Okay? So if you think of a column vector, x1, x2 down to xn, and column vector Rn can also be considered as a matrix with n rows and 1 column. This is an n by 1 matrix. N rows, 1 column. So in some sense, if you like, a matrix is a kind of a generalization or extension of the vector. That's what a matrix is. And the standard notation is as follows. The first row, let's say we use the letter A for the coordinates of the matrix, A11, A12, A1, let's say J, to A1N. This is the first row of the matrix, and there are n numbers in it. The second row, A21, A22, A2J, to A2N. When we get to the ith row, the first index on the subscript of the coordinate is the row. Second subscript is the column. This is AI1, AI2, AIJ, AN. Down to the last row, which is the mth row, AM1, AM2, AMJ, AMN. So this is the standard notation for a matrix, and this is the very important thing. You have to have this, get the subscripts right. AIJ Aij is the coordinate in row I, column J. So each coordinate is doubly subscripted, and the first subscript is the row, and the second subscript is the column. So this is the standard notation for a matrix. And M and N can be, in this matrix, the ith row, let's call this matrix capital A. The ith row of the matrix A is this, AI1, AI2, up to AIN. It's a row vector, if you like. The jth column of A, if you look at the jth column, it's a column vector. A1J, A2J, down to AMJ.
Hi, I'm not really understanding the AIJ. Can you explain more what that is?
It's just the number that's in this position in the matrix. A matrix is an array of numbers. Here is a 2 by 3 matrix. 2 rows, 3 columns. So if we were to call this matrix A, the entry in the first row, first column, A11, would be 7. First row, first column, the number is 7. A12, first row, second column is 2, and so forth. It just tells you where it's no different from, if you look at a vector, what is x2? X2 is the second number down in the vector. Right? Aij is the number in the ith row, jth column of the matrix. That's all it is. I mean, there's nothing there.
I have a question.
Hmm?
Hello?
Yes, there a question?
Yes. So I see at the end of the chart A equals. What is those letters at the end? AXN? Is that AXN? The last row?
The letter here,
Yes.
this is the mth row, nth column. So this is A, M, N.
And
the number in the mth row and nth column of the matrix.
then the one above is AXN?
There's no x's in this at all.
Okay, because I can't understand your handwriting a little bit. Above is
Right,
A.
but that's why there is this very carefully printed out textbook on Blackboard, which I'm following very closely and is legible. So if you pull up the textbook, you can always see exactly what's going on.
And what is the letters above? It says AIN?
Right here?
Yes.
Yes. So this is the ith row, row I, column N. So this is A, and the subscript is IN.
Okay. Thank
So
you.
for example, for if A is a 2 by 3 matrix, the first number would be A11, second number would be A12, A13. That's the first row. The first subscript tells you the row. Second row, A21, A22, A23. So it's just a matrix of numbers. So just the way a vector is a column of numbers. A matrix is a rectangle of numbers. And just as you can add and subtract and scale or multiply vectors, you can do the same thing with matrices. Let's look at the simplest case. Let's say a 2 by 2 matrix. Suppose A is the matrix 1, 2, 3, 4. Or just so you don't think these numbers have to be in order in any sense. Suppose, boy, let's make it more interesting. Well, let me just follow one example in the book. If A is 1, 2, 3, 4, 5, 6. This is a 2 by 3 matrix. Suppose B is another 2 by 3 matrix. 3 minus 1, 0, minus 5, minus 7, 8. So these are 2 by 3 matrices, and I can add them. And how do you add them? You add by adding coordinates, just the way with vectors you add coordinates. So in the first, look at this little box if you like, right? It's a 2 by 3 matrix. So there are 2 rows, each with 3 numbers. So what goes in the first row, first column position? Take what's in the first row, first column of these 2 matrices and add them. 1 plus 3 is 4. Second row, second column, 2 plus minus 1 is 1. First row, third column, 3 plus 0 is 3. Second row, first column, 4 minus 5 is minus 1. Second row, second column, 5 plus minus 7 is minus 2. Second row, third column, 6 plus 8 is 14. Suppose I want to subtract these matrices, A minus B. So it's just like with a vector, you subtract vectors by subtracting the coordinates. For A minus B, it's 1 minus 3 is minus 2. 2 minus minus 1 is 3. 3 minus 0 is 3. For the second row, 4 minus minus 5 is 9. 5 minus minus 7 is 12. 6 minus 8 is minus 2. These lines here. Erase them. So if this is the matrix A and this is the matrix B, this is A plus B and this is A minus B. And you can take a matrix, just as with a vector, you can scale or multiply a vector by a number. So for example, what is 7A? Let's multiply the matrix A by 7. The matrix A is 1, 2, 3, 4, 5, 6. You multiply a matrix by a scalar by multiplying every coordinate by the scalar. 7, 14, 21, 28, 35, 42. That's 7A. Any questions about this? Everything we do in this course is going to involve matrices. And so you need to learn these things as quickly as possible.
I have a question.
Yes.
How did you get the 7A equals? Can you explain that one more time, please?
Well, A is this matrix.
Okay.
7 is a number. Where did I get 7? I like the number 7. I pick it at random. Doesn't matter what number you pick. So if I want to multiply the matrix A by 7, this is the matrix A. The way you multiply by 7 is to multiply every number in the matrix by 7. 7 times 6 is 42, and so on.
Okay, thank you.
It's no different from matrix multiplication, from scalar multiplication of a vector. Okay.
Is it
And
possible?
all, question?
Yeah, is it possible to add a 2 by 3 with a 2 by 1?
No. You can only add matrices of the same shape. So you can add an m by n matrix with an m by n matrix, but you can't add an m by n matrix to a number where n is different. They have to have the same shape. That's a very good question. So what are some nice properties of matrix multiplication? So let A, B, and C be m by n matrices. Same number of rows, same number of columns. So one can check that all of the nice properties of addition hold. It's associative. So if you take A plus B and add C to that, that's the same as adding A to B plus C. It's commutative. A plus B always gives the same result as B plus A. There is an additive identity. So what we call the zero matrix, ZMN, every entry is 0. So it's the analog of the zero vector. ZMN is the matrix consisting of m zeros in every row, or sorry, n zeros in every row, m zeros in every, it's all zeros. And A plus the zero matrix, or the zero matrix plus A, just gives you back A. And if you let minus A or minus 1 times A, what is that? That's the matrix where you multiply every scalar by minus 1, just minus A11, minus A12, minus A1A, and so forth. So if you add A and this minus A, you always get the zero matrix.
I have a question.
Yes.
So the associative, the commutative, and the additional identity, is that just because that's the format?
What do you mean? No, I don't know what you mean by the format. I mean, it's
So can you explain?
it's the truth,
Because I didn't understand this page.
right? That is, if you take matrices A and B and you add A plus B, or if you add B plus A, you get the same thing. So for example, suppose A is 2, 0, minus 5, 1, and B is 3, 9, 8, minus 15, right? Those are two by two matrices. So what is A plus B? I add them. 2 plus 3 is 5, 0 plus 9 is 9, minus 5 plus 8 is 3, 1 minus 15 is minus 14. That's A plus B. Suppose I add B plus A. I get 3 plus 2, 9 plus 0, 8 minus 5, minus 15 plus 1. Compare these two. They're exactly the same. A plus B equals B plus A. That's just,
And that's what makes it commutative, because it's going to be the same.
that's the definition of commutative.
And associative?
Associative, this is the definition of associative. An addition of matrices is associative if for all matrices A, B, and C of the same shape, if you add A plus B and then add C to that, you get exactly the same as if you add A to the sum of B plus C.
So what's the difference between associative and commutative?
Does this line look like this line?
No.
This involves A, B, and C. This involves just A. They're different sentences.
Okay.
Like saying, what's the difference between saying a tree is tall and a rose is red? Well, they're different sentences. These are different sentences, different statements. They're not connected. They're just properties of matrix addition.
And where it says A plus ZMN, can you explain that, please?
Yeah. Well, Z is just a matrix where every number in it is 0.
Okay.
So this just says if you add the 0 matrix to any matrix A, it doesn't change. You still get back A. It's just like saying 6 plus 0 equals 6, right? You add the number 0 to 6, you get 6. If you add the matrix 0 to A, you get A.
And is it the same concept for where you have negative A equals negative one times?
I'm just saying, what is I define negative A or minus 1 times A. You just change the sign of every number in the matrix, every coordinate. Right?
Okay. And that computes to the one on the bottom, A plus negative A.
Yeah, I mean, like for example, suppose A was 1, 2, 3, 4. Then minus A would be the matrix minus 1, minus 2, minus 3, minus 4. And if you add A to minus A, you're adding the matrix 1, 2, 3, 4 to the matrix minus 1, minus 2, minus 3, minus 4. What do you get? 1 minus 1 is 0. 2 minus 2 is 0. 3 minus 3 is 0. 4 minus 4 is 0. That's all. I mean,
Okay.
we're not saying anything hard here. We're just saying, 1 minus 1 is 0. A minus A is the 0 matrix.
Thank
you. I mean, so all the properties you would hope would be the case are the case. And it's exactly the same thing with scalar multiplication of matrices. So if you have scalars, C and C prime, and a matrix A, if you multiply your numbers C and C prime, and then multiply the matrix A by that, it's exactly the same as taking the matrix A, multiplying it by C prime, and taking this matrix and multiplying it by C. It's like, for example, in this case, if this is my matrix A, and suppose C is 2, and C prime is minus 5. So C times C prime is 2 times minus 5 is minus 10. So C prime times A would be minus 10 times A. That's minus 10 times 1, 2, 3, 4. Multiply every coordinate by minus 10, you get minus 10, minus 20, minus 30, minus 40. That's C prime times A. What is C prime times A? C prime times A is minus 5 times A. You multiply every coordinate by minus 5. You get minus 5, minus 10, minus 15, minus 20. So what would C times C prime times A be? C is 2, and C prime A is minus 5, minus 10, minus 15, minus 20. When you multiply, you get minus 10, minus 20, minus 30, minus 40. It's exactly the same as that. So C prime times A is C times C prime A. Right? It's just saying what you would think is obvious if I didn't write it down specifically.
I have a question. I don't understand how you got those numbers.
It's just multiplication. It's just
So for instance,
what is here? What is 2 times minus 5?
negative 10.
Okay, so C prime 2 times minus 5 is negative 10. What is A? A is the matrix 1, 2, 3, 4. What does it mean to multiply a matrix by a number? You multiply every coordinate by the number. What is 1 times minus 10?
-10,
Okay, there it is. What is 2 times -10?
-20,
There it is. What is 3 times -10?
-30,
There it is. What is 4 times -10?
-40.
That's it. That's all. Just multiplying by a number.
Oh, okay.
No.
And then the same goes for the -5. You just times it by 8, which is 1, 2, 3, 4, and that's how you get your answers.
Yeah,
Whereas-
just multiply. It's just arithmetic. I mean,
Okay.
if it didn't sound like I was using fancy words like vectors and matrices and all that, you could give this to kids in elementary school to do. Oh, here's some numbers, just multiply them. And they would do it. Because they don't think it's hard. They would just do it. Right? That's all. It's kind of psychological. And just the way we have distributive laws in arithmetic, you also have distributive laws for matrices. If you have 2 matrices, A plus B, and you add them and multiply by a scalar C, that's C times A plus C times B. Or if you have a matrix A and you take the sum of 2 scalars, C plus C prime times A, that's CA plus C prime times A. But I mean, this might look complicated because I'm using letters and not numbers, but it's really nothing. So all this says is, remember what a vector space is. A vector space is a set of things, vectors, that you can add and multiply by scalars. And suppose we let matrices, MAT stands for matrix, MAT, MN of R. So this is the set of all M by N matrices with real coordinates. So you fix M and N, this is all M by N matrices, and this is an example of a vector space. Because just the way you can add vectors in Rn and multiply them by scalars, you can add matrices of the same shape and multiply them by scalars. So that is good to know. Now, there's one thing you can do with matrices, which you cannot do with vectors, which is in some cases you can multiply matrices. We did not define any way to multiply vectors. You can multiply a vector by a number, by a scalar, but we didn't define the product of 2 vectors. But there is a way to define a product of 2 matrices in certain cases. It's actually based on a kind of matrix multiplication of vectors where you have 2 vectors, and if they have the same dimension, then you can get a scalar when you multiply it. But let's suppose we have, so let A be an M by N matrix. So this has M rows and N columns. And suppose B is a N by P matrix. So in the matrix A, we have M rows and N columns. So in each row of this matrix, you have N numbers. In the matrix B, you have N rows and you have P columns. So in the matrix B, every row has P numbers But if you just look at the columns, every column has n numbers. So if you have an m by n matrix, every row has n scalars in it. In the matrix B, every column has n scalars in it. Right? So you have n numbers going across every row in A, and n numbers going down every column in B. Any questions about this? So suppose I take one row of A and one column of B. So this row is going to look like, let's say the coordinates of this are Aij. If I take the ith row, it'll look like AI1. Let me do it on a bigger piece of paper. On paper, I have some more room. Suppose I take row I from the matrix A and column J from the matrix B. So this ith row is a row vector, AI1, AI2, up to AIN. And the jth column of B is going to be B1J, B2J, down to BNJ. So the same numbers here and here. And what I do is I just multiply them the coordinate-wise and add. So I take the first number here, the first number here. That's AI1, B1J. Second numbers, AI2, B2J. I'm going to be adding. And I do this all the way along until I get to the last numbers, A, I, N, B, and J. So let's just look at this in some examples. Suppose I had n equal to 3. So this would be, let's say the row were 7, 2, 5. And the column were 3, minus 1, 4. So what does it mean to multiply this row by this column? I take 7 times 3, 2 times minus 1, 5 times 4, and I add. This is 21 minus 2 plus 20, that's 39. So this row times this column gives me the number 39. If they were two-dimensional vectors, suppose this were just 7, 2, and 3 minus 1. This would be 7 times 3 plus 2 times minus 1. 21 minus 2 are 19. So if you took Calc 3, this is just the dot product of vectors, which you used all the time in vector calculus. And the way you multiply matrices is to multiply these rows and columns at every place in the matrix. So let's just see if you understand. So here's an exercise for you to do right now. Compute the following products. Suppose I have 2 minus 9, that row, times the vector 1, 5. or take the row 3, 0, minus 1 times the column 4 minus 1 minus 9. What is that? Or do a four-dimensional vectors. 3, 0, 2 minus 1 times 7, 1 minus 1, 8. So take a minute and calculate what these things are. This times this, this times this, this times this. This is a two-dimensional times a two-dimensional thing. That makes sense. This is three-dimensional and three-dimensional, four-dimensional and four-dimensional. In every case, what comes out is just a pure number, a scalar. So work it out and someone tell me what you get.
For the top right column vector, is that a 4 or a 9?
This is a 9.
The top right column vector, the
Here?
yeah, is that a 4
That's
or
a
a 9?
4.
Okay, thank you.
The first one I got -43.
Right, so 2 times 1 is 2. 9 times 5 is 45. So it's 2 minus 45, which is minus 43. That's exactly correct.
The second one I have 21.
Let's see, 3 times 4 is 12. 0 times minus 1 is 0. Minus 1 times minus 9 is plus 9. So you get 12 plus 9 is 21. And in the four-dimensional case,
Almost done. 21,
I think I got 11 for that.
sorry,
11, I think.
let's see, 3 times 7 is 21.
done.
0 times 1 is 0.
It's
2
11.
times minus 1 is minus 2. Minus 1 times 8 is minus 8. So this is 21 minus 10, which is
11.
yes. Okay. So this is called multiplying a row into a column. That's how you do it. And once you understand or see how to do that, then we can define what is it, how and under what circumstances can you multiply two matrices. So let's see. So matrix multiplication is a skill that you have to develop. And the only way is to do a lot of examples by hand. And you check yourself by looking, you can look at some of the examples in the book, and then you do the multiplication. And if you get something different, find out where the mistake is. So suppose A is an M by N matrix, and B is an N by P matrix. So this says the number of columns of A equals the number of columns of B. When that happens, you can multiply them. Get a matrix A times B, which I'll call C, and C It will be like these n's cancel. C will be an n by p matrix. And the way this is defined is as follows. So suppose A is the matrix A11 up to A1n down to AM1 up to AMN. This is using the standard notation for the coordinates of a matrix. And A times B, let's say B is the matrix B11 to B1P, because the matrix B has P columns and it has n rows. So as you go down, the last row will be the nth row, Bn1 up to Bnp. So here in each of these rows, we have n numbers, and in each of these columns, we have p numbers. And the product will be this matrix C, which will be, as I define it in a moment, an n by p matrix. So this will have n rows, C11 down to m rows, m by p, the n's, CM1, and p columns up to C1p down to CMP. And if I take, and I want to know, what are these numbers? When I multiply A and B, how do I get the coordinate Cij, which is the coordinate in the ith row and the jth column? Okay. So if I'm going to say that there's a product of these two matrices, if A is an n by n matrix and B is an n by p matrix, and then I can multiply them to get an m by p matrix, I have to know what are all the coordinates in this matrix A times B equals C. What are the coordinates in the C matrix? What is Cij? And the answer is, you take the ith row of the matrix A. So this is the ith row, AI1, AI2, up to AIN. That's the ith row. Then I take the jth column in the matrix B, B1j, B2j, down to Bnj. This is the jth column. And I multiply them. And the ijth coordinate in the matrix C will be the product of this ith row of A times the jth column of B, which is going to be AI1 B1j plus AI2 B2j, all the way up to AIN BNJ. We're using sigma notation. This is summation. K goes from 1 up to n, AIK BKJ. This is the formula for Cij. And I'll give that a star because that is the definition of matrix multiplication in terms of coordinates. So again, this looks, I'm sure, a little bit abstract and maybe even difficult, but I'm going to start to do some examples. And when I do the examples, more and more examples, it should become clearer. But this is something you have to be able to do, and you have to be able to do by hand. I mean, there's literally no way to pass a course in linear algebra without knowing how to use matrices. So let's take what's always the simplest case, which is 2 by 2 matrices. So suppose, so this is the case of 2 by 2 matrices. So suppose A is, I don't know, 3, 7, minus 1, 8, and B is 2, 0, minus 5, 1. So this is a 2 by 2 matrix, and I'm going to let, so A is 2 by 2, B is 2 by 2. So if I let AB be C, the matrix C will also be 2 by 2. That is, I want to multiply 3, 7, minus 1, 8 times 2, 0, minus 5, 1. So I'm going to get a 2 by 2 matrix. I have to find the numbers that go into the 4 coordinate places. What goes into, this is the first row, first column number. So I multiply the first row by the first column. So this is going to be my C11, C12, C21, C22. What are these equal to? So C11 is going to be 3, 7, first row, times the first column of B, 2 minus 5. This is 3 times 2 plus 7 times minus 5. That's 6 minus 35. That's minus 29. So the number that goes here is minus 29. What is C12? What number goes into the first row, second column of the product? C12 is the first row of A times the second column of B. So that's 3 times 0 plus 7 times 1. That's 0 plus 7, that's 7. So the number that goes in here is 7. This is the second row, first column, C21. Second row, first column, I take the second row of A and the first column of B. That's minus 1 times 2 plus 8 times minus 5. That's minus 2 minus 40 is minus 42. So this number is minus 42. This is the coordinate in the second row, second column, C22. I take the second row of A and the second column of B. That's 0 plus 8 is 8. So when I multiply these two matrices, this is what I get. Okay. So let me pause for a moment, take a look at this and check the calculations. And if you have a question in a minute or so, you should ask.
Professor? He's here. Professor, are you here? Professor?
Yes.
For C21, I think
You got the answer minus 42. It's not 42, isn't it? 38 minus 38.
Let's see. C21. So it's second row minus 1, 8 times 2 minus 5. So that's minus 2 minus 40
Oh, okay.
minus 42.
Okay, I see. It's minus 40. Okay.
Any questions about this? Let's look at another example. This is one in the text. So suppose A is the 2 by 2 matrix 0, 2, 3, 0, and B is the 2 by 2 matrix 5, 0, 0, 7. If I add them, A plus B, you add coordinates, it's 5, 2, 3, 7. If I add them in the opposite order, A plus B, it still is 5, 2, 3, 7. So we see, as we mentioned previously, that A plus B equals B plus A. Matrix addition is commutative. Let's look at matrix multiplication. Let's multiply A times B. That's the matrix 0, 2, 3, 0 times the matrix 5, 0, 0, 7. This is going to be a 2 by 2 matrix. Let's see, what goes into first row, first column? You take the first row, 0, 2 times the first column. That's 0 plus 0 is 0. So you get a 0 there. First row, second column, 0, 2 times 0, 7. That's 0 plus 14 is 14. So here we get 14. First row, second row, first column. So the second row of A is 3, 0, and the first column of B is 5, 0. That's 15 plus 0 is 15. And second row, second column, I take the second row and the second column, that's 0 plus 0 is 0. So this is what AB is equal to. Any questions about that? You really need to check what's going on and step by step by step. Suppose I multiply in the opposite order. B times A. So B is the matrix 5, 0, 0, 7, and A is the matrix 0, 2, 3, 0. So this is going to give me what? Well, first row, first column, The first row of B is 5, 0, and the first column of A is 0, 3. When I multiply that, I get 0 plus 0. Get 0.
I think you'll get the same answer.
Well, let's see. First row, second column. So that's 5, 0,
0,
2, 0. That's 10 plus 0. This is 10.
Oh,
Oh, different.
yeah.
Second row, first column. 0, 7, 0, 3. That's 0 plus 21 is 21. 21 there. Second row, second column. Second row, second column. 0 plus 0 is 0. I got 0 here. So this is BA. This is AB.
Mhm.
This is BA. And we notice something extremely important here, that AB in this case is not the same as BA. They're different. They're different. So
I think it's when adding, they will be the same, but when multiplying, will be
sorry?
different. When you add them,
Yeah. When you add them, they're the same. That's what I did up here.
yeah,
But when you multiply them,
you
it's
get different.
possible they would be the same, but this proves that they're not necessarily the same. So matrix multiplication in general is not commutative. So this is a very important fact.
Mhm.
Let's look at a more complicated example. I'm also taking this directly from the text, so it's easy to check. Suppose A is a 2 by 4 matrix, 2 rows, 4 columns. Let's say A is the matrix 2 minus 3, 1, 0, 5, 0, minus 4, 1. And suppose B is a 4 by 3 matrix. So B is going to have 4 rows. I'm just going to write it here. So this is B. 4 rows and 3 columns. First row is 1, 2, 4. Second row, 0, minus 2, 7. Third row, 3, 1, 0. Fourth row, minus 1, 5, 3. So this is 2 by 4, A. 2 rows, 4 columns. B is 4 by 3. 4 rows, 3 columns. And the number of columns of A equals the number of columns of B. And if AB is the matrix C, C will be a 2 by 3 matrix. So I have 2 by 4, 4 by 3. The number 4 here is the same as the number 4 there. So you can multiply these matrices, and what you get, the shape of what you get when you multiply them, it's like the 4s cancel, it's just going to be 2 by 3. So this is going to be a 2 by 3 matrix. By
I'm
the
sorry,
way,
can you explain one more time why it's a 2 by 3?
well, So what I said and what I'm defining is with matrix multiplication. See where I did this? Well, in general, if you have an m by n, so you can only define two, you can multiply two matrices when the number of columns of the first is the same as the number of rows of the second. So if A is m by n and B is n by p, the product C will be m by p. This is how I'm defining matrix multiplication in such a way that this happens, right? I mean, this is, you might say, suppose you let x equal 3, and you say, no, I don't like x equal 3, I like x equal 4. Well, that's fine. You're allowed to like x equal 4, but we're starting with x equal 3. Here, we're defining matrix multiplication for certain pairs of matrices. You can multiply matrices A and B. The definition that I give, that everyone gives, the definition of matrix multiplication says if you have a matrix A with n columns and a matrix B with n rows, you can multiply them and you end up with an m by p matrix where A was m by n and B was n by p. So here I have it, I start with A as a 2 by 4 matrix. B is a 4 by 3 matrix. 4 and 4, they're the same, and the result will be this times this, 2 times 3. This is the definition of matrix multiplication.
Thank you.
Right? 2 by 4, 4 by 3, the result will be 2 by 3. So this will be some matrix which has 2 rows and 3 columns. I have to find the numbers that go into these 6 places. So for example, this is the first row, first column. So I take the first row of A, 2 minus 3, 1, 0, times the first column of B, 1, 0, 3 minus 1. What do I get when I multiply this row into this column? I get 2 times 1 plus minus 3 times 0 plus 1 times 3 plus 0 times minus 1, which is 5. So I get a 5 here. The number here is a 5. Right? This row into this column, and I multiply the row into the column, I get 5. What number goes here? This is first row, second column. So I'll be multiplying the first row, 2 minus 3, 1, 0, into the second column, 2 minus 2, 1, 5. 2 times 2 is 4, minus 3 times minus 2 is plus 6, 1 times 1 is 1, and 0 times 5 is 0. So this is 11. Get 11 there. What goes here? First row, third column. Take the first row of A, the third column of B. I multiply, I get 8 minus 21 plus 0 plus 0. 8 minus 21 is minus 13. What goes here? This is the second row, first column. So I take the second row of A, 5, 0, minus 4, 1, times the first column of B, 1, 0, 3 minus 1. I get 5 plus 0 plus minus 5 plus 0 minus 12 minus 1 is minus 8. Get a minus 8 there. And I just continue. to get the entry in the second row, second column, I take the second row into the second column. I get 10 plus 0 minus 4 is 6 plus 5 is 11. And to get the second row, third column coordinate, it's the second row into the third column. This is 20 plus 0 plus 0 plus 3 is 23. So if I multiply this 2 by 4 matrix times this 4 by 3 matrix, I get this 2 by 3 matrix. So matrix multiplication satisfies many of the same kinds of properties as multiplication of vector of numbers satisfies and so on, but not the commutative law for multiplication. I do need to mention one very important matrix. So an n by n matrix. This is a matrix with the same number of rows and columns. So a rectangle where the length of the side and the height are the same, it's called a square. So an n by n matrix is also called a square matrix. So 1, 2, 3, 4 is a square matrix. 1, 2, 3, 4, 5, 6 is not a square matrix. Here the number of rows equals the number of columns. Here it does not. And one very special and important n by n matrix is called the identity matrix. And that's the matrix, it's a square matrix with ones down the main diagonal. That is, let's see, here's like the 3 by 3 identity matrix. 1, 0, 0, 0, 1, 0, 0, 0, 1. The main diagonal of the matrix is the set of numbers where you start with the upper left-hand corner and then go across 1 and down 1, across 1 and down 1. This is the main diagonal. And the identity matrix is the matrix where the numbers in the main diagonal are 1 and every other number is 0. And this can be defined or expressed in terms of what is called the Kronecker delta, which we use all the time in linear algebra. Delta, that's the Greek letter delta ij, is defined to be 1 if I equals j and 0 if I is different from j. So this matrix 1, 0, 0, 0, 1, 0, 0, 0, 1 can be expressed using the Kronecker delta. This is delta 1, 1, delta 1, 2, delta 1, 3, delta 2, 1, delta 2, 2, delta 2, 3, delta 3, 1, delta 3, 2, delta 3, 3. Because the way this Kronecker delta is defined, down the main diagonal, the subscripts are the same. So these are ones. Off the main diagonal, the subscripts of the delta are different. I is different from j, so it's 0. So this is the Kronecker delta, which is something you need to. Here, let's start with an exercise that you should do and then I'll do just to get some practice. Let's suppose that A is a square matrix, an n by n matrix. Then A squared means exactly what you think it should mean, A times A. And A cubed is A times A times A. And A to the fourth power is A times A times A times A. If A is n by n, all of these powers are defined in general. A to the k, you multiply A by itself, k times. So here's a calculation for you to do right now. And then I'll do it and we'll check and see if we get the same result. Let's take my favorite simple matrix, 2 by 2, 1, 2, 3, 4. So compute A squared, which is A times A, and A cubed. Of course, A cubed is A times A times A, but it's also A squared times A. So to compute A cubed, once you've calculated A squared, just multiply A squared by A. So A is 1, 2, 3, 4. A squared is 1, 2, 3, 4 times 1, 2, 3, 4. So calculate that and see what you get. And then A cubed, let's say this is A times A squared. So that's 1, 2, 3, 4 times whatever you got there. So do this calculation. I'll stop for a minute. What is 1, 2, 3, 4 times 1, 2, 3, 4? Find that matrix, then plug it in here and find A cubed. So, did anyone calculate this A squared yet?
I got 7, 10, 15, 22.
Let's see. So for the first row, first column, 1 plus 6 is 7. For the first row, second column, 2 plus 8 is 10. That's good. Second row, first column, 3 plus 12 is 15. Second row, second column, 6 plus 16 is 22. So that's exactly right. So then to calculate a cubed, which you can write as a times a squared, that's 1, 2, 3, 4 times 7, 10, 15, 22. So next you have to calculate a cubed.
Wait, how you got 15? Sorry.
Sorry,
How you got 15?
second row, first column. So second row
First
of
column.
A times the first column of B is 3 plus 12 is 15.
Oh, I see. 15. 6. 7.
So this is a little bit, this calculation is what? First row, first column. First row times the first column is 7 plus 30 is 37. First row, second column, take the first row of A, second column of A squared, that's 10 plus 44 is 54. Second row, first column, take the second row of A, and the first column of A squared, that's 21 plus 60 is 21 plus 60 is 81. And second row, second column, I take the second row of A, second column of A squared, that's 30 plus 88 is 118. So that's what I got. I have to say, matrices come up everywhere. They come up in almost every profession. You will see them in accounting, you'll see them in nursing, you'll see them in biology and chemistry and physics. It's really a fundamental algebraic object. And you need to spend as much time as necessary to become friends with matrices, familiar with matrices. That's the goal. And so I would spend a lot of time, this is all in the notes, in the printed textbook. I would spend a lot of time studying the examples, and you don't have to wait for the homework assignments. You can be doing problems as soon as possible just to get skilled dealing with matrices. It's really an essential text. Any questions about this? So this is where I'm going to stop. There's a lot more to do, but since many of you are seeing matrices for the first time, it may be a lot to absorb at once, but we have 5 days until the next class, at least, so there's plenty of time to look at this.
I have a question.
Yes, sir. Yes, go ahead.
Here you did a times a squared. Would it be the same thing if we did a squared times a?
Yes.
So it's only commutative if it's 2 by 2.
No. I mean, the previous example that was not commutative was still 2 by 2. Sometimes it happens that matrix multiplication is commutative, but most of the time it's not. And the lesson is that you cannot assume that matrix multiplication is commutative. It may happen to be, but generally it's not, right? It's like if you flip a coin, you might get a head 3 times in a row. But you can't assume that every time you flip a coin 3 times, you're always going to get 3 heads. It can happen, but it doesn't necessarily happen. That's all. Sometimes it happens, sometimes it doesn't. All right. Next class is Monday morning. See you then. Have a good weekend. All.
Professor, you said the following Monday there's no school. And
Not this coming Monday, a week
yeah,
from
I
now.
know, the week from that.
Yeah.
And you said Tuesday we will have class on Tuesday?
I know, sorry, the one Tuesday I know we have class. We're also closed on Columbus Day, which I think is October 9th.
Yeah, so
There's
that
a class
Tuesday
on
on the
Tuesday,
10th.
October 10th.
Yeah, that's a Monday schedule. Okay.
Yeah,
So not not next Monday.
right. But we do have math this coming Monday.
Yeah.
That is, today is the 13th.
Mm.
So we have class on Monday, the 18th.
The
But we
20th.
do not have class. School was closed on Monday, the 18th. Sorry, on Monday, the 25th.
Yeah. All right, thank you.
Okay. All right. Bye, all.